This is the first of two lessons on electron configurations. This first lesson will simply be some of the rules or principles that go into writing electron configurations, and the second lesson for this PowerPoint or this topic will be on actually writing the electron configurations. The learning targets that go along with writing the electron configurations you can see here, and in this first video we'll simply be hitting this first learning target. We want to be able to explain the three principles that govern ground state electron configurations. So jump right into it. What is an electron configuration, or more specifically for this class, ground state electron configurations? We've used that term ground state already in learning about atomic emission spectra, and we know that the ground state refers to the lowest possible energy that an atom can have. So a ground state electron configuration is the lowest possible energy arrangement of electrons in an atom. In other words, what that tells us is it tells us which energy level or levels, sublevels, and orbitals electrons are found in for each element. And there are three principles that determine or dictate these electron configurations. They are the Aufbau Principle, the Pauli Exclusion Principle, and Hund's Rule, and we'll look at each of those individually in this lesson. The Aufbau Principle. The word Aufbau comes from the German language meaning to build up or to construct, and what it tells us is that each electron in an atom will always occupy the lowest energy orbital available. So in other words, we start with the lowest possible energy orbital and work our way up from there. Thus the term Aufbau, again meaning to build up or construct. Within any energy level, the order of the energies would go the S sublevel first, followed by the P, then the D, and then the F. So within any single energy level, that's always the order they would fill in. S, then P, then D, then F. The problem is, this next point, is that sublevels from other energy levels will overlap. Just as an example of what we mean by that, the 4S sublevel, that is lower in energy than the 3D sublevel. So even though 4S is in the fourth energy level, it actually fills before the 3D sublevel because that orbital is lower in energy than the 3D orbitals are. Now you might be thinking, well, how will I ever remember that, and are there other overlaps? Yes, there are all sorts of overlaps, but you don't need to memorize any of it because there is a handy chart or a rule that we can use to remember them. The order of this filling, in other words, the order of the energies, is given by the northeast to southwest rule. And we have a picture of that here. Just to explain what you're looking at here. Notice all of these sublevels are listed by their number and letter designation, and notice all the S sublevels are in the first column. So we have 1S, 2S, 3S, 4S, 5S, etc. And then we put the P's in the second column, and notice there is no 1P listing because, as we know, there is no 1P orbital. So we start with 2P and just list it down. And then the same thing with the D sublevel and then the F sublevel. I'll explain what the blue is over here in just a second. And then as far as why we call this the northeast to southwest rule, notice the arrows that are drawn in here diagonally. If you think about a compass with north being straight up, these arrows are drawn from the northeast, so the top right hand corner, to the southwest bottom left hand corner. And we simply draw in an arrow through each diagonal of the chart. So the first arrow only goes through 1S, as you can see here. The second arrow only goes through 2S. But then that third diagonal, it will cut through 2P and then 3S. The next arrow would cut through 3P and 4S, and so forth. If we simply follow the order that the arrows cut through each of these sublevels, that gives us the order that the sublevels will fill in. So all we do is we start with the first arrow, and that cuts through 1S, so the first sublevel to fill is 1S. Then we go through the second arrow, that's 2S. Then it would be 2P, and then 3S. After we're done with that arrow, then we go to the top of the next arrow, 3P and 4S, and you just keep going with this. So if we simply write all that down, it would look like this. The order of the filling, and you can see it here, just following each arrow from top to bottom, 1s, 2s, 2p, etc., all the way up through 7p. And notice that is the last sublevel that any arrow cuts through on here. These sublevels that are listed here in blue are simply here because those sublevels do exist, but we never use them for ground state electron configurations. None of these sublevels or orbitals within the sublevels ever have any electrons in them for ground state electron configurations. So they really would not have to be there for this chart in order for us to use it correctly, because we would never use them anyway. But you could put them there if you wanted to. Now, before you go on to the next slide, what I would ask you to do here is to practice drawing out this chart. This is not a chart that will be given to you on a quiz or a test, but you're welcome to use it as long as you can produce it yourself. So just practice drawing out this chart, and then from that, make sure you can get this order that you see listed over here for the order of sublevel filling. So just take a few minutes, practice drawing out the chart and drawing in the arrows, and then from the arrows, practice writing out this order and make sure it matches this exactly as you see it here. The next rule or principle that guides our electron configuration writing is called the Pauli Exclusion Principle. The Pauli Exclusion Principle says that no two electrons can have the same set of 4 quantum numbers, that's N, L, M sub L, and M sub S, simultaneously. Now that 4th quantum number is not one that we have dealt with much in class, in fact hardly at all so far. This is kind of the first time we're really going to see it. That is known as the electron spin magnetic quantum number, and you can see the notation for that is the lowercase letter m with the subscript s. And there are only 2 possible values for m sub s. They are either plus 1/2 or minus 1/2. Those are the only 2 values we can have for that quantum number. Now, just to clarify what we mean by electron spin, you can think of it as an electron spinning like a ball, but that's not really what it is. The electron, because its charge it has an electric charge, and because it's always moving, moving electric charges produce magnetic fields. And so what this electron spin magnetic quantum number tells us, it's related to the direction of the magnetic field of the electron, or the magnetic field that's being produced by that electron moving. And there's only 2 possible directions for that. You can think of them as positive and negative, or up and down, and we symbolize that by using the plus 1/2 and the minus 1/2. So just an example of how this Pauli exclusion principle works. Let's say we were going to fill the 1s sublevel with electrons. Now recall that the 1s sublevel, like any s sublevel, only has 1 orbital, and that would be described by these 3 quantum numbers. N would be 1 because it's 1s, L is equal to 0 because it's an s sublevel, and then M sub L has to be 0 because L is 0. So that's why there's only 1 orbital there. Now the picture you see at the bottom, you see there's just a box there labeled 1s. This is what is called an orbital box diagram. We just draw a box to represent the orbital that is in the 1s sublevel. Now if we're going to put an electron in this s sublevel, the electron would have what we would call to be positive spin. Positive spin, and we indicate that by using the plus 1/2 for the electron spin quantum numbers you can see listed over here. Also notice that these first 3 quantum numbers, those match exactly that we set up here for this orbital, because this electron is in this orbital. Now we can show that on our diagram by drawing an up arrow. The up arrow simply indicates the electron with positive spin. In other words, M sub s is plus 1/2. Now, based on the Pauli exclusion principle, if we were going to put a second electron in this orbital, it has to have negative spin, because all 4 of these numbers cannot be the same. The first 3 are going to be the same because it's in the same orbital. So the only thing that can be different is that electron spin quantum number, so that has to be minus 1/2. So if we were to add that to our diagram, we would just draw in a a down arrow, and that indicates an electron with negative spin. Now ask yourself, is there any way that we could put a third electron in this diagram and not have it match one of these sets of quantum numbers here? The answer to that question is no, because the first three quantum numbers have to be the same because it's the same orbital, and the fourth quantum number, there are no other options. There are only two options there, either plus 1/2 or minus 1/2. So this is it. There are no other possibilities. This is why, as we have already learned, that there can only be a maximum of 2 electrons in any orbital. Because if you were to have a third electron, then the set of 4 quantum numbers would be exactly the same, and that is not allowed. The final principle or rule that determines electron configurations is known as Hund's rule. And Hund's rule says this, that single electrons with the same spin must occupy each degenerate orbital before pairing electrons with opposite spins in the same orbital. Recall that all orbitals in the same sublevel are always degenerate. Just remember that the word degenerate means exact same energy. So a couple of examples there. If we're talking about the 3p sublevel, all 3 of those 3p orbitals are degenerate. They have the exact same energy. Likewise, we could say the 5 3d orbitals are degenerate. And you could say this about any orbitals as long as they're in the same sublevel. They're always degenerate. So an example of what this statement means, I understand this statement's kind of wordy and lengthy, and we'll see exactly how this is applied here. Let's say we are going to fill the 4d sublevel. And I'm going to use an orbital box diagram like we just saw. Notice here there are now 5 boxes. The reason there are 5 boxes is because we have a d sublevel, and as we know, d sublevels contain 5 orbitals, so each box represents a different orbital. If this sublevel were just to have 1 electron in it, we would put that electron in the first orbital with a positive spin. We always start with the first orbital we can, always with a positive spin. If we were to put a second electron in it, there are a few options. We could put that second electron in the first orbital with a down spin or a negative spin. As we just saw in the last slide, it can't have 2 of the same spin. That's not allowed. We could put it in a different orbital with the same spin. So say we put it in the second orbital with a positive spin. Or it could have a negative spin. And it could go in any of these orbitals with an up spin or a down spin. Well, according to Hund's rule, it says that single electron, so just 1 electron, with the same spin, so this, we already have a positive spin here, so the next electron will also have a positive spin. The same spin must occupy each degenerate orbital. So the next electron will go in the next orbital with a positive spin. If we were to have a third electron, it would go in the next orbital with a positive spin. A fourth electron, again, the fourth orbital with a positive spin. Fifth orbital, fifth electron with a positive spin. Only once we get each orbital with an electron in it all with the same spin, then do we go back and we start pairing up electrons. So if we were to have a 6th electron, that would go in the first orbital and that would have a negative spin, because as we just saw, we can't ever have the same spin in the same orbital. And then we would just continue this. A 7th electron would pair in the second orbital, an 8th electron would pair in the third, a 9th electron would pair in the fourth orbital, and a 10th electron would complete that sublevel and pair in the 10th orbital. The reason why this is it deals with the stability of the atom. As it turns out, the more you can maximize the amount of spin or the magnetic field, the more stable the atom is. So by having all these electrons first with positive spin, that maximizes the amount of spin that we can have, and then those end up getting canceled out because we put in these negative spins. So that's why we always pair them not until after we get each of the orbitals filled. So that completes this learning target. We have explained the 3 principles that govern the ground state electron configuration. It also ends this lesson. In the next lesson, we'll look at these next 2 learning targets of writing these ground state electron configurations and drawing out orbital box diagrams.